Welcome back, everyone. We are starting section 10.2. This is actually one of two videos on section 10.2. And we're going to talk about using calculus when it comes to parametric curves and equations. We know that when we take the first derivative, this is actually the tangent, or the slope of the tangent line is our derivative function here. And now because y is now a function of t and, x is a function of t and y is a function of t, when we take the derivative of y, that's going to be with respect to t over derivative of x with respect to t. So we're going to have two functions, derivative with respect to t, derivative with respect to t, and they're going to be over. Now, it's very easy to mix these up. We often take the derivative of x first and inadvertently putting it into the numerator, and that clearly is not going to work here. Now, the second derivative is a little more tricky. So here's the second derivative, and when we break it up by pieces like this, this is saying take the derivative with respect to x of the derivative of y with respect to x. And because we have to introduce t now into this, we now end up with this. Is our derivative. And what we're going to end up doing as we apply, here's our derivative operator here. And now I could have brought that, well, let's do this now. I'm going to take the dx and the dt and I'm going to swap them out. And believe it or not, this is the final product of, of the second derivative. Now, let me break this down just a little bit on what we're doing here. This says after we find the first derivative with respect to x, we're now going to apply the derivative function to that new function that we got from here. And it's still divided by the dx dt. So this is going to be best explained with an example. So let's skip to it. Example 1. Show that C has two tangents at the point 3, 0. Now here's our actual curve. And what we're going to be looking at here are these tangent lines. Let me just kind of emphasize it a little stronger. This line here and this line here. And what we're looking for is the slope of these tangent lines. And we're also going to find the actual equation of these purple lines here. So let's get started. Part A. Show that C has two tangents at the point 3, 0. So let's start out with our two functions here. Here's our x is a function of t and y is a function of t. I'm going to start out by finding dx dt, which is 2t. Now remember, that's the denominator, not the numerator. dy dt is 3t squared minus 3. So our slope function is going to look like this. And what we're going to need to do is get us some t values here. Well, I know when x equals 3, replacing the x with a 3, I get here. And this gives me that t is equal to plus or minus the square root of 3. Now when y equals 0, we get 0 equals, plugging it into here, t cubed minus 3t. Which means t minus 3 equals 0. This means t equals 0, that's t squared there. And so that means that t is going to be plus or minus root 3 again. Now, these two jive, the 0 does not. So it has to be solutions to both. So at t equals 0, we're not going to use that one as having a tangent that we're interested in. Now, you can see at 0, we actually have a vertical tangent. We'll get to that. So what I'm going to need to do now is if t equals root 3, then I want to see what the points are. I want to see what the slope is. So m is going to be 3 times, oops, I'm over here, sorry. That's going to be 3m equals 3 times root 3 squared, which is just 3, because the radical and the squared cancel, minus 3. Down below, we have 2 root 3. Let's see what we get from there. That's going to be 9 minus 2, that's 6 over 2 root 3, or 3 over root 3, which is actually just root 3. So the slope over here, this is a positive slope, and you can see here's my positive slope. That's going to be a positive root 3. And let's see what we get if t is equal to negative root 3. Let's see what that slope becomes. Squaring the negative root 3 is still just going to give me 3 times 3 up here, minus 3, and then over negative 2 root 3 when I plug in that t, the negative there. And using the same simplification process, we end up with negative root 3 as our slope there. So our slope for this line is negative root 3. So we have 2 lines, and now we need to find the equations of these lines at this point here. So the first one, so we'll call this one L1, we'll call this one L2. So L1 is going to be y minus 0 equals root 3, so that's the positive radical there, times x minus 3. This gives us y equals root 3x minus 3 root 3. So this is our first equation of a line with a slope, root 3, and a y-intercept of negative 3 root 3. And you can see that here's 0, right? So that's going to cross down here somewhere. Let's get our second line. Y minus 0 equals negative root 3 x minus 3. So there's our second line. And you can see that the y-intercept for this one is going to be positive, right? It's going to be crossing up there. All of that just for part A. Part B. So show the points on C where the tangent lines are horizontal and vertical. Okay, let's start with horizontal. That means the slope equals 0. Now I want to point out that we have horizontal tangent slopes right here. So I'm guessing we're going to end up with the points 1, 2, 1, negative 2. We will see. So when the slope equals 0, I'm going to go back up to my slope function here. And that basically is saying, when is the numerator equal to 0? And divide a 3 out, I get t is going to be plus and minus 1. So let's see what point that ends up being. All the way up to here. So when so we'll do t equals 1, I'm going to get x equals 1 squared, which is 1. Y equals 1 cubed minus 3 times 1. That's going to be negative 2. So the point 1, negative 2. 1, negative 2 is right down there. And when t equals negative 1, again, plugging those into here and here, x equals negative 1 squared, which is a positive 1. Y equals negative 1 cubed minus 3 times negative 1. Now, negative 1 cubed is a positive 1, is a negative 1, pardon me. And that becomes plus 3, or positive 2. Giving me the other point is going to be 1, 2. We can see that right there. So let's talk vertical. That's when m is undefined. So that basically is, when is the denominator equal to 0? So I'm going to take the denominator. And we can see we have a vertical tangent line right there. And when t equals 0, when you plug that into here and here, here and here, we're going to get that x and y are both at 0, 0. So the point 0, 0. And again, our graph, everything's jiving together here. And see if we can squeeze C into here. C is asking for determine where the curve is concave upward and concave downward. For that, I'm going to need the second derivative. So I'm going to use this here. The numerator is going to be my derivative function, this one here. And I'm going to take the derivative of it with respect to t. And then the denominator will still be 2t. Now, I'm going to use some scratch paper to do this. So I'm going to take our derivative function here, and I'm going to rearrange it a little. So m because, which is dy over dx, I'm going to pull a 3/2 out. And I can factor our 3 out, make it over 2. So that's t squared minus 1 over t. That's going to be t minus 1 over t. And what's going to happen is I'm going to go ahead and take the derivative of that with respect to t. It's going to give me 3/2 and then 1 minus, plus, pardon me, 1 over t squared. So now we're here. And so my slope function, or my second derivative, this is my numerator, 3/2, and then 1 plus 1 over t squared over 2t. 2t, that's my derivative right here. There. So I'm going to try to fix this up a little. I'm going to pull the 3, and it's now over 4 because of that 2 there. And this is going to be 1 plus 1 over t squared over t. So that is going to turn into, to save a little space, when we clean all that up, multiply the top and bottom by t cubed, we end up with 3/4 t squared plus 1 over t cubed. So I'm just going to take all that work I just did and just write it down here, just because I'm low on space. Now, what that's going to become is we need to know when this is positive and when it's negative. Well, I'm hoping that you can see that the numerator is always positive, because any real number squared is going to be a positive value plus 1. So the main thing that's going to determine negative or positive, concave up, concave down, is going to be t itself, t cubed. So this means that so t cubed is going to be the determining factor. And so when t is positive, t is bigger than 0, then concave upward. Because when t is positive, that's going to be positive, making the whole thing positive, making the whole thing concave up. When t is negative, then the denominator is going to be negative, making the whole thing negative. Then that means that it becomes concave downward. And we can reflect on that, but I am going to move on to the next example. So let's take this here and talk about the cycloid. And here's the function for a cycloid. please note that x is now a function of theta, and y is a function of theta. So our parameter in this case isn't t anymore, it is now theta, which is fine. So part A, find the tangent to the cycloid, and there's the formula, at the point where theta equals pi over 3. Cool stuff. So let's start out by finding dy d theta. So that's this one here. Dy d theta is just going to be r sine theta. Because remember, the derivative of cosine is negative sine, so negative, negative. And dx d theta is going to give us r times 1 minus cosine theta. Now I want to point out, notice that that is y. So they're actually derivatives and antiderivatives of one another. So our tangent slope is here. So remember, dy d theta goes up top. And you'll note the r's reduce out. Remember, we want to evaluate this at t equals pi over 3. So sine of pi over 3 is root 3 over 2 over 1 minus, and sine of pi, or cosine of pi over 3 is going to be 1/2. I think it's root 3 over 2 minus 1, which is just root 3. So our slope in this case, again, totally different problem, happens to be the same number, is root 3. Now we need to find points x and y at pi over 3. So now I'm going to take the pi over 3 and plug it into here and into here. So x of pi over 3 is r pi over 3 minus 3 over 2. X, y of pi over 3 is going to be here, r 1 minus 1/2. So that's actually going to be 1/2 r. So plugging this into y minus 1/2 r equals root 3, and then x minus x is here, all of that. You see our point slope form there, and I'm just going to stop there. And in case you're curious of what formula I used for the line here, it's this one here. So there is our messy answer to part A. Let's go to part B. At what points is the tangent horizontal and vertical? Now horizontal, we know that's when the numerator is equal to 0. So this means that theta is going to be 0 or pi. We'll just do one cycle. I didn't state it explicitly, but we'll go from 0 to 2 pi. And now I do want to point something out, that when I plug in 0 here and here, I'm dividing by 0. So I get 0 over 0. So we're actually going to not include that. Now, it's going to be vertical. So this is horizontal. Horizontal slope. And the vertical slope is when the slope is undefined. Slope, not slope. Which means that's where the denominator is equal to 0. And cosine is equal to 1 at theta equals 0 and at 2 pi, which is outside of our range here. So here are, to make up our horizontal slope and our vertical slope. All right, let's talk area. Now, traditionally, when we're talking about area under a curve with calculus, we have y dx, where y is some function of x. We're going to keep to that. The thing is, if y is just going to be the g of x, right? That's y. Dx is going to be, so dx is going to be f prime of t dt. And you can see that is there. And you can see what this here is here. Now, I use Greek letters here. This is alpha and beta, because it's not the same as A and B, meaning alpha and beta have to be t values. So we are going to find the area under one arc of a cycloid. Here's the cycloid here. And by the way, from the previous problem, we can see at pi, we have a horizontal asymptote, and at 0 and at 2 pi, which we didn't need, we also have a vertical asymptote. It's undefined there. All right, so let's do this. Theta for this problem is going to go from 0 to 2 pi inclusive. And we are going to use the integral, so what area of one loop, so 0 to 2 pi, is going to be 0 to 2 pi. And that is going to be y, so that's going to be r, 1 minus cosine theta, times f prime of t, which is x, is the derivative here. This is going to be times r, 1 minus cosine theta, d theta in this case. All right, so I have r times r, which is a constant. I'm pulling that out in front. And I end up with 1 minus cosine squared d theta. So I'm going to go ahead and FOIL that out. Minus 2 cosine theta. I'm going to break this up. So this is going to be r squared times theta from 0 to 2 pi minus 2r squared sine of theta from 0 to 2 pi. And this is going to become plus 1/2 r squared, the integral from 0 to 2 pi, of 1 plus cosine of 2 theta d theta. So I'm going to handle each of these three pieces separately. Now the 1/2 comes from the formula, or cosine squared. So here, when I plug in 2 pi and 0, I get 2 pi r squared minus, here's the good news, sine of 2 pi is 0, sine of 0 is 0. So this whole thing here goes to 0. Now we're here. This is 1/2 r squared theta from 0 to 2 pi. Plus, I'm going to get an extra 1/2 from there. So that's going to be 1/4 r squared sine of 2 theta from 0 to 2 pi. And again, very nicely, when I plug in 2 pi or 0 there, this whole thing goes to 0. So this becomes 2 pi r squared. Plugging in 2 pi there, make it minus. Plugging in 2 pi there, I'm going to get just pi r squared. And plugging in 0, of course, goes to 0. And then I'm noticing that should be a plus because there's a plus there. I mistook for that one there. And we end up with 3 pi r squared is the area. So all we're going to need to know what the actual area is of any given one is the radius of the circle that's rolling along. All right, that is the end of part 1.